Hello students, welcome to this very next screencast. This one is about special systems of linear equations. So all the real world problems that we're going to be looking at today need to be set up as a system of linear equations, and we begin. This one is about speed ice climbing. I did not know that was a thing either, but apparently it is. Two people are training for a speed ice climbing event. Here's the first, here's the second climber. During a practice climb, one climber starts 15 seconds after the first climber. That's an important fact. We'll get back to that in a moment. The rates that the climbers ascend are shown. Here are the rates. We're going to use those numbers in just a moment. Let d be the distance in feet traveled by a climber t seconds after the first person starts climbing. Write a linear system that models the situation. We'll do that. And then we'll answer the question, based on the linear system, does the second climber catch up to the first climber? And then we'll explain why or why not. Alright, so let's begin. They give us some very crucial information right here in the second paragraph. Let d be the distance in feet traveled by a climber t seconds after the first person. So what we have here is we see that d is going to be our distance traveled in feet, and time is going to be t. Of course, in seconds. And remember, it's t seconds after the first person starts climbing. So that's going to be a very important fact in just a moment. What we need to do is create an equation that represents the ascension rate for each of these climbers and keeping in with their times as well. So let's start with the very first climber. So the first climber, which we'll call this guy right here, all right, is climber 1. It appears that he climbs 10 feet every 30 seconds. So let's talk about his rate. He is climbing at 10 feet every 30 seconds. Well, you know, one thing that we like to do is we like to put things into their unit rates. And you might recall a unit rate is when the denominator is not, well, in this case out of 30, but out of 1. And so one thing we can do is think about this. If this climber climbs 10 feet in 30 seconds, well, that would mean he is climbing at a rate of 1 foot every 3 seconds. Very good. But still, if he's climbing at 1 foot every 3 seconds, another thing we could say is that he's climbing 1/3 of a foot for every 1 second he is ascending. So there you go. We have our rate. The first climber is at 1/3 feet per second, and we're going to use that. We're going to use that significantly. Alright, so knowing that is very valuable, why don't we put this whole thing off to the side here? That way we have it to use later on. Alright, so we'll put it right there along with our other important information. We still have to make the equation for climber 1, and in order to do that, we have to think about something that we've probably known for a while. How do you calculate distance? Well, distance is equal to, it's a very famous formula, RT. Distance is equal to the rate multiplied by time. And the rate, by that we mean kind of a speed. And in this case, we're talking about feet per second. So d is equal to RT is a very, very famous formula. And we are going to create two formulas. One, d equals RT for climber 1, and another d equals RT for climber 2, which we'll do in just a moment. Now we're focusing just on climber 1. So we don't know the climber's distance. That's what we're trying to figure out. So the equation that we're looking for climber 1 is going to be d equals, in this case, his rate, which we just calculated as 1/3, multiplied by t, the time, which again is completely unknown. So d is equal to 1/3 multiplied by t. Distance is equal to rate times time has now become distance is equal to 1/3, which is this climber's rate, multiplied by some unknown time. And there we have the first equation for climber 1. You know, we would have also gotten this 1/3 if we had just started with 10 feet per 30 seconds by saying d is equal to 10 feet every 30 seconds. That's also technically a rate, a speed. It's just not in what we consider to be, you know, lowest terms, multiplied by t. But of course, as you can see, once you simplify 10/30ths, you will get 1/3. So it's both the same thing. Alright, so we're going to use this one, of course, because 1/3 is easier to work with. Thus, we have climber 1's first equation. Alright, so let's take all that good information and place it over here to the side. Climber 1's equation is d is equal to 1/3 t, and we're still going to use d is equal to RT as we talk about climber number 2, which is this guy right here. Alright, so we got to make his equation now as well. We're going to use same techniques, alright? Well, now look at the information for climber number 2. It says, this climber climbs 5 feet every 15 seconds. Alright, so instead of climbing 10 feet every 30 seconds, he's going 5 feet every 15 seconds. Something's interesting about that compared to climber 1. Perhaps you see it. Well, let's look at something here. That would mean he climbs 5 feet every 15 seconds, but we don't want to know how many feet he climbs in every 15 seconds. We'd rather put this into, of course, lowest terms. Well, if he's climbing 5 feet every 15 seconds, that means he's ascending at a rate of 1 foot for every 3 seconds again, just like climber 1 as we saw right over here, which, as we saw from before, this means he's climbing 1/3 feet for every 1 second that he is ascending. So notice that we have the exact same rate, the exact same speed for both climbers. So based on that, we can now set up his equation. So what we can do is take his information, let's kind of shrink it down there so we can use it later and give ourselves some more room. His is going to be, of course, we're going to make a d is equal to rt equation for climber number 2 now. And in order to do that, distance is equal to his rate, which is, of course, once again, 1/3, multiplied by t. However, his quote-unquote t, his time, is quite different than climber number 1 because we go back to the instructions and we notice that during a practice climb, one climber starts 15 seconds after the first climber. So the second climber is starting 15 seconds after the first climber. We, of course, still need to multiply it by whatever his time is. Well, his time is not just t, because t, as we see here, represents the seconds after the first person starts climbing. So how many seconds after the first person has climber 2 began climbing? Well, that's 15 seconds afterwards. So if t represents the time, 15 seconds after that would be t minus 15. So we take the time and subtract 15 seconds from it. And this entire expression, t minus 15, represents the time right here. So his rate is 1/3, his time is t minus 15 seconds, which, of course, we can, of course, take 1/3, multiply it by t, by distribution, and then 1/3 times negative 15. So his equation is going to be 1/3 t, 1/3 times t, and 1/3 times negative 15, of course, we know, is negative 5. Thus, we now have the equation that represents climber's 2 distance. So we're going to use that. Okay, so now what we see here is we have both climbers' equations. We have climber 1's equation, d is equal to 1/3 t, and climber 2's equations, d equals 1/3 t minus 5, based on all the information that we just spoke about. Let's put this into a true-looking system of linear equations. Let's stack these on top of each other. So this is climber 1, and this is climber 2. So we'll put his over there, and let's make this just equal sizes, if we may. Alright, beautiful. Now we're able to put this all together. There, that's much more organized. Now, knowing that we have both of these equations, let's start using them. Let's give ourselves a little bit more room right here. Alright, now, how should we solve equations? Well, we have 3 ways that we've learned of, and more exist, and we have yet to learn more ways, which we will do. But, let's see here. We have these 2 equations. We need to solve for both d and t, if possible, of course. Remember, this is about special systems of linear equations. So let's see here. We could use graphing if we wanted to. I mean, clearly we have our slope and we have our y-intercepts, negative 5 and, well, 0. And graphing would do it. It certainly would. But, you know, I'm a fan, in this case, I think I'm going to use substitution. Because I noticed that for at least one of the equations, in this case it's both, one of the variables is already kind of, sort of, quote-unquote, solved for. In fact, both of them are. So what I'm going to do is I'm going to take this section, which d is equal to 1/3 t minus 5, and I'm going to replace it into this d right here in the other equation, because d is equal to 1/3 t minus 5, so replacing this d with 1/3 t minus 5 should prove no difficulty and is mathematically sound. So like I said, I'm going to take this whole thing, which is 1/3 t minus 5, and I'm going to send it into d right there. So let's do a little bit of rewriting here. So this now becomes 1/3 t minus 5 is equal to 1/3 t. And you might see from this point here something kind of strange is going on. So in order to solve this, well, what we have to do is, the rule has been the same ever since last year in 7th grade. You want all variable terms to one side and all constants on the other. So I'm going to go ahead and move this 1/3 t over to this other side here. And in order to do that, I of course have to subtract 1/3 t to both sides. And look what happens upon doing that. What remains on the left here but is nothing more than the number -5. And what is 1/3 t minus 1/3 t? Well, we saw the same exact phenomenon happen over here. 1/3 t minus 1/3 t, of course, is 0. So what are we left with? We're left with -5 is equal to 0. That's weird because we know from our heart of hearts that is not true at all. Thus, we see that this particular system has no solution. Now, what does that mean in the context of this problem? We have to further explain what the no solution actually means. And in order to do that, we have to look back at the situation. Well, the situation, remember, was as follows. We had 2 climbers, speed ice climbing, and one climber starts 15 seconds after the first climber. We saw pretty early on that both rates were exactly the same. If somebody climbs 10 feet every 30 seconds and another climber climbs 5 feet every 15 seconds, they are climbing at the exact same rate of 1/3 feet for every second. So if they're both climbing at the same rate, but this first climber, as we saw, starts 15 seconds early, then the second climber, who's climbing at the exact same speed, the exact same rate, is 15 seconds behind him, is never going to catch up unless he speeds up his rate, which he doesn't. He's still climbing at the same exact rate as the first climber. So if they're both climbing at the exact same speed, the exact same rate, and one is 15 seconds behind, well, that means he's never going to catch up, ever. He's got to speed up his climb, which he's not doing in this case. Thus, we cannot find the solution. In other words, there's never going to be a time where the second climber catches up to or gets ahead of the first climber, because he's always going to be 15 seconds behind. Poor guy. And that, ladies and gentlemen, is how we interpret what the no solution means in this particular system. All right, very good. Very, very good. Now it's time for yours. Yours is definitely a fun one as well. This one is about roller rinks. Yes. I don't know if you've ever been to one, but they do still exist. They are rare. One admission to a roller skating rink costs X dollars, and renting a I want to go to a roller disco. Cool. Oh, sorry. Where was I? Renting a pair of skates costs Y dollars. A group pays $243 for admission for 36 people and 21 skate rentals. Another group pays $81 for admission for 12 people and 7 skate rentals. Is there enough information to determine the cost of one admission to the roller skating rink? And please explain why or why not, based on your mathematics, and do interpret it within the context of this situation. So, there you have it, folks. Your problem, please set it up as a system of linear equations and solve it using any of the 3 methods that you wish, but no matter what, if you do your math correctly, you will come to all the same conclusion. All right. Good luck, everyone, and let me know if you have any questions.